So the first thing I think we need to understand is all of chapter 2, that's weeks 2, 3, and 4 in this class are vector related, right? So it's very, very crucial for you to understand what vectors are. So I think we should kind of start off by just going over a couple of definitions. So vectors are a type of physical quantity that have magnitude and direction. So when I say magnitude, what do you think of, or do you understand what that term is?
That means the length, right?
Not just length. We represent it as a length, but that doesn't necessarily mean it's a length. A magnitude it's a value, basically. It doesn't have to be related to space. It just has to be related to a value.
So we could say a scalar value.
Yeah. So for example, you can say that somebody is big, right? Big is a magnitude. Doesn't even have a number attached to it, right? It's just a magnitude.
Okay.
I like to think of size when I think of magnitude, but that's probably not correct because it's not just size. It can be size, it can be temperature, right? It can be anything that has a value that you can quantify.
So in the case of vectors, we just use length as that size.
Yeah, we use it as a way to kind of visualize it for us. So a vector has a magnitude, and a magnitude is anything that you can quantify. And if it makes it easier for you, I like to think of quantifying in terms of comparison. So I say, if I'm not sure if I can quantify something, the first thing that I ask myself is, can I compare it to something else? So if I'm looking at the size of a car, or I don't know, not the size, let's do something else. I'm looking at the horsepower of a car. I want to say, can I compare the horsepower of one car to the horsepower of another car? The answer is yes. Okay, then that's a magnitude. Does that make sense?
Yeah, so you can compare the length of a vector to the length of another vector.
Yeah. So vectors have magnitudes, just like any other scalar quantity, but they also have direction, right? And this is what makes vectors different, or direction without the S. This is what makes vectors different to other physical quantities. They have magnitude and they have direction. So because they have the direction, they have to be pointing somewhere, right? So whenever we think of vectors, there's kind of a mathematical way of thinking about them. I'm going to try to leave those till the end of the chapter, but then there's a more of a graphical way of thinking about them. And that's kind of what I want to focus on the first couple of weeks. There's a physical definition of vectors, but I think that the physical definition kind of becomes obvious as you start doing problems. But in this particular chapter, we're going to look at force vectors. Those are going to be kind of like the main ones. There are other types of vectors. You have velocity vectors, you have position vectors, you have many different types of vectors. So anything that you can assign a magnitude and direction to, that's a vector. So
Will we be getting into those?
What?
Will we be getting into those other types of vectors? Okay.
Yes. So you kept saying that magnitude was kind of like the length of the vector, and that's right. In terms of, what is this? That's kind of right when we're talking about, oh, that did not work at all.
Yeah, no, I can't see it now.
I use the cheapest materials I can find, how it should be. That's right when you're talking about graphical representations, because the way we're going to deal with vectors is we're going to represent everything graphically. So when we're talking about, and I'm not going to use force because we're going to use force through the entire chapter. So let's think of velocity. When I'm talking about velocity, I'm looking, for example, at a particle that's moving from one position to another position. So let's say that this is the position at time equals 0 seconds. And here's the particle's position at time equals 1 second. Okay, so at 0 seconds, the particle is here, it moves, and at 1 second later, it's here. Okay. So if I'm looking at the velocity of this particle, I can represent that velocity as a vector. At 0 seconds, the vector is kind of pointing, it's always going to point tangent to the curve of the particle, right? So at 0 seconds, let's say that this is my velocity vector. Okay?
Yep.
When we express this as a graphical entity, I'm not saying that the particle is going to move from here to here, right? And I'm not saying that the particle is moving along a straight line.
That's just the direction it's moving at that moment.
At specifically this time, right?
Okay.
So this is just a graphical representation. It doesn't mean, this is not related to space, right? It doesn't mean that the particle will move through space through this line. It doesn't, right? It just means that at this particular time, this is my direction. And then because I'm using a graphical representation, I can use the length of this vector to represent the magnitude of the vector, right? So we can give this this magnitude a length, and let's say if this is a length for velocity at time 0, I'm going to call it v naught, v0.
Okay.
When I say naught, I just mean sub-0, right? V sub-0.
Yep.
And let's say that at time equals 1 second, the velocity vector is
v sub 1.
v sub 1, yep. So just from the graphical representation, at which time does the particle have a higher velocity? Just looking at it graphically.
V sub 0.
Exactly, right? So we assign a length as a representation of the magnitude of the vector, then that means that the lengths will be proportional to the magnitudes. So you can identify the larger magnitudes by looking at the larger lengths. But again, one thing that I think a lot of students get confused is that this is just a graphical representation. It's not a physical one, right? Doesn't mean that the particle moved more here and less here. It's just that this is faster because I'm drawing a bigger arrow. This is slower because I'm drawing a smaller arrow. Now,
so if you flipped it, you could just flip it and say that it moves. I mean, that wouldn't make sense, but you could just make the v sub 1 longer.
Yeah.
And then that would be the higher magnitude.
Yeah, exactly. And this is just a graphical way of looking at it, right?
Mm-hmm.
Physically, the particle just moves from here to here. And at some point, its velocity decreases from here to here, right? That's physically what's happening.
Mm-hmm.
Graphically, we're just identifying them with arrows. So that's the first thing. The reason we want to identify vectors with arrows is because one very interesting thing about vectors is that they behave like geometric shapes. And that's really, really helpful because the fact that they behave like geometric shapes means that we can use graphical or geometric methods to actually identify vectors and their properties.
So like the sine law, cosine rule,
yep.
Triangle rule, parallelogram law, all that.
All that stuff, yep. And this is really helpful. Like I sometimes get frustrated because I really, really want to stress how helpful this is. And sometimes we don't, even when I was a student, I didn't understand it. When I was a student, I was like, okay, yeah, so we can use triangle rules. That's okay. But it's actually really helpful. The fact that you can represent these quantities, these velocities, you can represent them as geometric shapes, helps a lot. And that's where all these, all these laws like parallelogram law, triangle rule, sine law, cosine law, all come into play. Now, the things we need to understand for vectors before we start, I'm going to work on problem quickly, but before we work on problems, I will say that it's always important to identify what represents the magnitude and what represents the direction.
Okay.
So I always like to think of vectors as products of magnitudes and directions. In other words, I can look at this.
Because you multiply theta times, sorry, my voice went out.
Yeah, go ahead.
Because you multiply theta times the magnitude.
Yeah. So that's pretty much the way I like to look at it.
Times the cosine of theta, usually.
Yeah. And you don't have to look at them that way, but I think it will be helpful to think of vectors as things as products of magnitudes and direction. So for example, this V naught, I can consider this V naught as being the product of two things. So I can say that V naught is the product of a magnitude, and I'm just going to call that magnitude V naught. So notice that I didn't use the arrow. This is just a value. I'm just going to give it a number. Let's say that this is 3 meters per second. So V naught, the vector, I see it as equal to 3 meters per second, right? But that's just a scalar. We need a direction. So times an arrow that points in that direction. That's the way I look at it. And that arrow is your theta, right? Mm-hmm. This isn't something that you have to do, but if you always look at vectors as products of magnitudes times direction, then this will be helpful when we're doing vector operations and when we're resolving vectors into components. Because essentially that's all that vectors are, products of magnitudes and directions. We can multiply vectors just like we multiply any other number, right? So if I multiply 2 times V naught, really all I'm doing is I'm taking V naught and I'm multiplying the scalar value by 2.
Mm-hmm.
So it's the same thing as saying if V naught is 3 meters per second in this direction, then 2 times V naught should be equal to 2, right? Times
3
your,
meters per second.
exactly.
But do you also multiply it times the error in that case, or is it scalar times scalar, theta times theta always? Okay, so you multiply it times all of that.
Yeah.
I see. Because
So
you're multiplying it times the entire vector.
exactly.
Okay.
So what you end up with is 2 times 3, you know, this is 6 meters per second,
Mm-hmm.
times your direction.
Mm-hmm.
So it's actually the same direction, but it's going to be twice as big, right? Typically, this coefficient, the 2, is what we call a scale factor, right? Because you're essentially scaling the vector, right? I'm making it twice as large.
Mm-hmm.
If I multiply by 3, I make it 3 times as large. If I multiply by 0.1, I'm making it 1/10 of its size, right?
Mm-hmm.
So addition is a little bit different, right? When we're adding vectors, and here's where we start coming into new territory. When we're adding two vectors, we need to consider that they have magnitude and direction, so we can't just add the scalar values completely, right?
Yeah.
So what we're going to do when we add two vectors, I'm going to give you two random vectors. Vector 1, vector 2. Adding them is a little bit easier to do graphically, because if I want to add vector 1, I'm just going to call this, not B, let me call it A. Vector A and vector B. If I want to add them up, I say A plus B equals, all I have to do is start with one vector and follow it with the next vector, right? And then the line that connects the end of the first vector to the tip of the second vector.
Is it R?
Yep, that's my resultant. I can call it R, I can call it C. When it comes to forces, I'm going to call them R, but really you can call it whatever you want. So if I say that A plus B equals C, then C will be that line that connects the end of A to the tip of B. Okay?
Okay, I see.
So addition is pretty much stacking one vector after the next.
So would you say free body diagrams are probably like the most helpful thing in this class?
There will be, especially when we're talking about forces. And we're going to go over free body diagrams in chapter 3. So at least you're one step ahead there. But they will be very helpful.
I just have realized that I can't really understand any of these concepts, and same for physics, unless I do like a diagram of everything involved.
Yeah. One thing that you want to note about addition is that, you know, when you add numbers, it doesn't matter which order you add them in, right? 2 plus 3 equals 5, 3 plus 2 equals 5, right?
Mm-hmm.
All right, so same thing with vectors. A plus B equals C, and you notice that C is kind of this diagonal vector, but I can also do B plus A, and it will be the same vector. So if I say B plus A, I'm going to start with B. I'm going to add A to it. And then C will be the line that goes from the end of B to the tip of A. And you'll see that it's the same vector. Obviously, I didn't draw them to scale, but it's essentially the same vector, right? Mm-hmm. Doesn't matter which one you add first or any of that.
Because it's communicative.
Mm-hmm. So that's the thing with vectors. You want to see them kind of like graphically as arrows with some length and some direction, or you can see them mathematically as simple arithmetic operations. Either way, you should be fine as long as you see them that way. You said you tried the fundamental problems, is that right?
Yeah, I got through the first one, and then I had to grind on the homework for that week.
All right, so if you did get through the first one, let's just go over the second one then.
Okay. Which page is it on again?
28.
All right. So F2-2?
Yep.
Okay. So two forces act on a hook, determine the magnitude of the resultant force.
Yeah, so it's very similar to the first one, so I think you should be able to understand that quickly, but let's just make sure that we get it. Before I start this, what's your time limitations? Like, when do you have to leave?
I mean, it's Saturday, so I'm going to grind on homework all day. You can take as long as the time you have.
All right, in that case, I'll be the one that determines when we leave because
Yeah, that works.
I don't want to spend all day here.
No, for sure.
Nothing against you.
I'm trying to get as much help as I can. So
yeah, no, it's fine. So we're going to have two vectors, okay? We have a 200 Newton vector, and that vector is pointed at 30 degrees from the horizontal, and then we have a 500 Newton vector that is located or pointed 40 degrees away from the 200 Newton vector. Let me write my directions quickly. Got my horizontal line, I got 30 degrees, and then I got 40 degrees. So this is what they are giving us, and it looks like it's not clear again.
I can see it pretty well.
You can?
And I wrote it down as well, but for the sake of the recording, you can't really see 30 degrees or 40 degrees right now.
So this is 30, this is 40, basically.
Yeah.
We want to find the magnitude of the resultant force. Now, resultant vectors are essentially added vectors, right? It's vector addition. So if we want to find the resultant force of 200 and 500 newtons, all we have to do is add up this 200 Newton vector plus this 500 Newton vector. So that's essentially what they're asking us. Now, the thing is that you can't just say 200 plus 500 is 700 and that's it, because that's not the way it works. You see that vector additions, you need to consider that vectors are scalars times direction. So you can't just add the scalars up.
You have to consider the direction of both as well.
Exactly. So I would say that the easiest way to solve this problem is graphically, right? And if you want to solve this graphically, then to add these two vectors is simply to draw one and then draw the next one, right? That's essentially how you would solve this graphically.
I could draw the 200. It does, once I'm like drawing them graphically to connect them, their direction in the original graph doesn't matter, right?
Exactly.
Okay.
So as long as the angles are the same, right?
Yeah.
You should be fine.
So I could draw the 500 Newton first.
Okay.
And then connect the tip of it and then have the 200 Newton going up. I'm drawing this on my own paper at the same time as well.
That's good.
That's why I'm talking through it.
That's good. So
and
you started with
200
500
Newton going up from the tip of, I started with 500 Newton.
Okay. So let's say you started with your 500 Newton vector, and then you drew your 200 Newton vector. Just from the drawing, you can see that the 200 Newton vector is a little bit more towards the horizontal than the 500 Newton vector, right?
Yeah.
Okay. Let me try to draw these again because I didn't draw them very clearly. I'm going to start with my 500, and I'm going to exaggerate the angles just for the sake of presentation. So I got my 500 newtons, I got my 200 newtons. Now, the first thing you can see is that I didn't really draw them to scale, right? My 200 newtons is drawn larger than my 500 newton.
Yeah.
So because of that, I'm really going to rely on geometric operations.
Yeah, because it doesn't have to be to scale.
Exactly. If I would have drawn them to scale and I would have drawn the angles correctly too, all I have to do is draw a line and measure the length of that line, and that's my answer. Right? That's how we solve it graphically. But because I didn't draw them to scale, I'm going to have to rely on geometry.
We're not going to solve these graphically in most cases anyway, because that would take over a long time, right?
Yeah.
Okay.
And also, any mistake in drawing, it's going to give you a bad...
I don't want to have a ruler and have to measure out every single
Exactly. If you have your two vectors and you're adding them up, then where does your resultant vector show up? Like the resultant of 200 and 500.
Wouldn't it be... I want to say that it would connect from the tip of 200 to the beginning of 500, but that's not right.
It would be the other way around, right?
Okay.
Yeah, the other way around. Remember, vectors will always end, or resultant vectors will always end at the tip. And that's kind of confusing because I call this the end and I call this the tip.
Yeah,
but
it's kind of confusing.
It is, yeah, because vectors begin at the end and end at the tip. But I don't know, if you want to give them a different name, then that's fine.
I'm just looking at the ones at the top. That makes sense.
Yeah.
It's just a bit more interesting when they're not like exactly perpendicular to each other.
Yeah. So this is my resultant vector, and that's really what I'm looking for, right? what I have here is a triangle. And again, it's a triangle that's not drawn to scale. So I can't just come with a ruler and measure it because I didn't draw it to scale. Instead, I got to rely on what I know from geometry. Okay. And here's where all these laws and stuff come into play. So before you try anything, I would say the first thing I want you to make sure you know how to do is make sure you know what angles you can get from this drawing. Because notice that this drawing gave you the angle for 200 from the horizontal and for 500 based on 200, but those aren't the angles in this triangle, right? So
yeah,
just looking at this geometrically, how do you think we can use this information, this 30 and 40 degrees? How can we use them for this?
I'm just trying to think about where those angles are outside of the triangle in relation, because if it's on the opposite side of like a line, like right beside 500, we could just move it across. So like for the 40, I'm just trying to think of it graphically because we changed not the direction, but the placement of them. Maybe I should have started with the 200.
Yeah, let me draw this triangle a little bit bigger.
Okay.
You're good. The good thing about this is that it doesn't matter which vector you start with, right? Your answer should be the same.
Yeah, just trying to think about where to put the angles is harder.
Yeah, but it's fine that you started with 500 because the book gives you the answer with 200, starting with 200, right?
Okay.
So now we're just doing it a different way, but we'll get the same answer, okay? So I'm gonna try to draw this a little bit bigger and try to exaggerate my changes in direction a little bit more, just so that we can look at those angles. Okay, let's say we have a triangle there. So the idea is we go back to this drawing and we figure out, okay, I'm just gonna start with what we have. We have a 30-degree angle from the horizontal to my 200 Newton vector, right? So where is that angle here? This is my 200 Newton vector. It's my 500 Newton vector. So where is that 30-degree angle? It's from the 200 Newton vector, right? To what?
It's from the 200 Newton vector to the horizontal.
Okay. So I can do two things, right? I can draw my horizontal here and say I have 30 degrees here, right?
Oh, okay, yeah.
I could also draw my horizontal here and I have 30 degrees here.
Does it matter? Well, we would get the same. We could take both of the angles there. If we drew the horizontal at the bottom, we could just say that the other angle is that too.
Exactly. Because remember, you have two parallel lines. This is the horizontal, right? Two parallel lines. So that means that this angle and this angle should be the same because we have parallel.
Geometry was like the first B that I got in the math course, so it's coming back to bite me. I didn't think it would.
It is important. That's why I teach geometry at a middle school, and I love it because it's so important.
Yeah, geometry is very important.
So
it's just unfortunate that I realize that now.
Yeah.
But oh.
Yeah, I always tell my geometry students that this is what gets my college students the most, like just that geometry.
Yeah.
But yeah, basically
the laws and the rules and stuff. Okay,
yeah.
But yeah.
You have two parallel lines.
Right there is 30 degrees.
Yep. You have two parallel lines. These two angles are going to be the same. And similarly, these two angles are going to be the same, right? So that's kind of one of those geometrical theorems. So we found where our 30 degrees are, at least, right? So now we have a 40-degree angle between the 200 vector and the 500 Newton vector.
So if we drew the vertical on that picture, like behind or to the left of in that picture, the 500 Newton, we know that from the horizontal to the vertical, it would be a 90-degree angle, and we have two of the angles. So we could find all of them.
Let's do that. So you're saying draw a vertical here?
Yeah.
Okay, so I have my vertical here, and let's say I have a horizontal. And you're saying, what do we know? Do we know this angle or do we know this angle?
We know the angle inside the triangle, and we know the angle from the horizontal to the resultant vector.
All right, I want to be careful with that. How do you think we know the angle inside the triangle?
I'm just trying to look at the graph and give the same orientation, but it's kind of hard. I was thinking because the 40 is where it is, and then we have the vertical, which is the angle to the left of 500 Newton.
Mm-hmm.
I was talking about it on the diagram
Okay.
of the hook and everything.
Okay. Yeah, so if you look at the diagram, you're saying we draw a vertical line, right?
Yeah, and then we can figure out that angle because we have 30 and 40. So
Okay.
it's 180 or 90 minus 70, so that's 20 degrees.
Okay, so we have that
I'm trying
angle.
to figure out where to place that in
Yeah,
here.
so this is my 500 Newton vector. This is my vertical.
Yep.
And in between, you're saying we have 20 degrees, right?
Yep.
Okay. This is my 500 Newton vector. This is my vertical, right?
Mm-hmm.
So in between, just like you said, we have 20 degrees. I'm assuming that's what you're saying, right?
Yes, that's what I'm saying.
Good. So we have that. We have a little bit more than we can use. We also have the...
Oh, well, we have the angle there now, so we could use the parallel lines.
Yeah.
So the angle...
Good. So that means that if we draw a parallel line here, vertical here, what is this angle?
20 degrees.
Okay. And what's the angle between a horizontal and a vertical?
That might be what gets me. The angle between a horizontal and a vertical is 90 degrees. So...
Okay. You got it, you got it.
Oh, because we can just assume that now.
Well, we're not assuming it just is,
because
right?
we drew two straight lines now, so
Yeah.
we can say that.
Yeah, I specifically drew my horizontal line and I drew my vertical line, and you know the angle between them is going to be 90 degrees.
Okay.
Okay.
So we have one small triangle.
Yep, we have one angle, right?
Yep.
Okay, cool. So what is that angle?
The angle where?
This angle inside the triangle.
Oh, well, that's 140.
Okay. So we already have one angle for the triangle,
Yep.
right? And that angle is going to be 140 degrees. All right.
Yep.
Cool. So we're starting off on a good foot, right? We know that we have 140 degrees, and we have two sides. We can still try to figure out other things, but for now, this should be enough for us to work with.
I don't know if we need to. We can probably use the law of sines now.
We could use a law of sines, yep. Or another thing we could use is we could just calculate this resultant directly with the law of cosines. That's right, so if you write down the law of cosines, let me just draw this triangle. If you have a triangle with sides A, B, C, corresponding angles little a, little b, little c, then the law of cosines says that c is equal to the square root of a squared plus b squared minus 2ab cosine of little angle c. And you might want to check that and correct me if I'm wrong, because I'm not really looking, I don't have my notes with me, but I think that's pretty much the law.
I'm pretty sure that's correct.
Yeah.
So it's kind of like Pythagorean theorem.
Yeah, well, the Pythagorean theorem comes from this law, right? Because in the Pythagorean theorem, we're looking at right triangles. In a right triangle, my angle C would be 90. The cosine of 90 is 0, so all this goes away, and you end up with the Pythagorean theorem. Mm-hmm. It's the same, right? So now the question is, do we have A, B, and little c? So do we have two sides and one angle?
Yes.
Okay. So in this case, I'm just going to give them names, right? I'm just going to call the 201A. I'm going to call the 500 Newton vector B, and I'm going to call my unknown vector C. And that way you can see that you have C, and the corresponding angle is the angle opposite to the side. So
which is 140.
140 would be my little c. Okay? So now I can just use the cosine law to solve this, right? So let's just go ahead and do that. And I'm just going to write the numbers here, but I'd like for you to calculate it because I don't have my calculator with me.
All right.
So I have for A, 200 newtons. For B, I have 500 newtons. And for C, I have 140 degrees.
I want to be in degree mode for this, right?
Yeah, because we're using degrees, right?
Yeah. Okay. Let's write this down. Cosine 140. Okay. Let me calculate that. So we got 2. Cosine 140. Okay. 665.74.
Okay, let's keep it to 3 sig figs. So let's say 666, right?
739. Oh, okay. 3 sig figs in total. Okay.
Yeah. And what are the units of that?
Newtons, because
Exactly.
we calculated the magnitude.
Yep, now you're good. Yep, because you're going to have Newton squared, Newton squared, Newton squared, and then take the square root of that, you get newtons for your units.
Yep. Okay.
Okay, so essentially we did it, right? We drew a triangle.
Mm-hmm.
We used geometry to find the triangle, and I'm not sure if you realize the hard part, not the hard part, but what took the longest in this problem was the geometry, right? It wasn't necessarily the vectors.
By far.
Yeah, and that's why it's really important for you to know your geometry, right?
Mm-hmm.
But that's essentially the basics, right, of calculating resultant forces or resultant vectors. These are vectors, and in this particular problem, they represent forces, but really they can represent other things, right? So instead of calling these forces, I could have just told you that I have a car, maybe not a car, but I have a plane or something, or a rocket moving at 500 miles per hour,
Mm-hmm.
and then switches direction 200 miles per hour. And I can ask you, what is the average velocity of that rocket?
And it would be the same thing.
Exactly the same thing. Okay, so it's not just about forces, right?
And when we switch to velocity vectors and everything, it'll be very similar.
It'll be the same. It'll be exactly the same procedure. So if I didn't include my units here, we wouldn't know that we're talking about forces.
Yeah.
Right, everything else.
Because we're talking about newtons, is that we know.
Yep. So that's essentially the basics. I think I need you to understand geometry. Okay.
Yeah. I'll definitely review on geometry.
Yeah. If you look at the fundamental problems, if you can, try to solve all of them. If you can't, look at the ones that look very different. So number 3, it's pretty much another version of number 2. So I would skip that one if I were you.
Kind of the same thing.
But try to look at problems or fundamental problems that look different. The good thing about fundamental problems is that their answers are in the back.
Yeah, that is very helpful.
Yeah, but sometimes the solutions aren't complete. So for example, for this one, the solution only included these last 2 steps.
Well, that's not very helpful at all.
Exactly, right? So you want to make sure that you understand, because this is the tough part of these problems, right? You make sure they understand this part.
Yeah.
Let me see. It's 10:40. I think I have a few more minutes.
Yeah, I don't want to take all your day. I appreciate you very much meeting me on a Saturday. I know that it's not really your work time, so.
Yeah, it isn't, but it's okay. It's okay. I just came back, so I'm still behind on grading and stuff. So I got a lot of work to do. So it's fine. It's not like I was going to do something different.
I think the hard part for me on this, definitely the geometry for sure, because I don't remember all my geometry stuff. But if I did that by myself, it would take me a long time to figure it out. And we have a lot of problems on the test, so that's just kind of tough.
Well, this is just one way of solving this, right?
Yeah.
There's another way that we look in chapter 2, and that's breaking down vectors into their components.
But this way makes a lot of sense to me. The component, not method, but just breaking it down into components does make sense. But I kind of like the geometrical method more because I can figure out where everything comes from.
Yeah, you do whatever's easiest for you. The component method essentially is giving you one vector and having you break them down into these 2. So I would give you C and its direction. And I would say break it down into a vector in this direction, a vector in this direction. And then you have to calculate these 500 and 200. It's,
Mhm.
you know, it may be a little bit more work, but essentially you're doing the same work but backwards.
Okay, so I just need to figure out how to do that as well because both of those will be on the test, right?
Yeah.
Okay.
So let's just do it with this one because we already know what the answer is going to be. So if I were to give you my vector c, and you already know that c is 666 newtons, right?
Mhm.
And we could figure out the direction, right? Because you already know these three sides. You can use the sine law to get this angle. And once you do that, you'll have the angle between C and the horizontal, right? So let's just go ahead and do that quickly. I just want this angle, right? And this was A, this is going to be an angle little a. So sine law tells me that sine of little a over A is equal to sine of little c over C, right? That's the sine law.
Mhm.
So I want to find A, this angle A, and I say that this angle A is equal to the, let's see, the inverse sine of sine of C. And what's C? C is 140 degrees times A, that's 200 newtons, over C, that's 666 newtons. Remember that we're using degrees. What does that give me for A?
11.13.
Okay, let's do 11.1. So that means that this is 11.1. So now can you tell me the angle between C and the horizontal?
Between C and the horizontal.
Yeah, this is my angle.
Oh yeah, yeah. So it'd be 90 minus 31, so it'd be like 69.
Yep. So 90 minus 20 is
I
70.
could do it exact, but
Minus
oh shoot, it's like
3,
I'll do it
68.
without rounding. Oh, sorry, 58. 58.8, so 59.
Okay. I'm just going to call it 58.9 just for consistency, okay? So I have this. So let's say that I give you your C, which is 666 newtons, and I say that it is at an angle of 58.9 degrees from the horizontal. And now I'm starting with this, and I want you to break down this vector into two components, right?
Mm-hmm.
A component along this line, which is 20 degrees from the vertical. I think that's what we got for B.
Mm-hmm.
And then a component along another line, which is 30 degrees from the horizontal. So I got another line here. And this one is 30 degrees from the horizontal. Okay?
So all of this would be given?
Yeah.
Okay.
Yeah, if you want to break down a vector into components, you need to know the direction of those components.
Yeah.
I can say break it down into its x and y components, and you know that x is horizontal, y is vertical. But here I'm not saying x and y. Here I'm actually giving you directions, specific directions. So
So in this case, would you break down each of the vectors into their x and y components?
it's not necessary. You see,
Okay.
when you have a problem like this, you solve the first problem using the graphical method, right?
Mm-hmm.
I think if you solve the first problem using the graphical method, you should be able to solve the second problem using the graphical method. So what I would do is the following. I'm going to start at the end of the vector, right?
Mm-hmm.
And then I'm going to pick one of these two directions. Which one do you want? The 30 degree or the 20 degree one?
20 degree.
Okay, so I'm going to pick that direction, and I'm just going to draw a line along that direction, okay?
Okay.
Just draw it as long as you can, okay? So that I started with my 20 degree line, and I drew it at the end of my vector. And now I'm going to take the other line is a 30 degree line, and I'm going to draw it at the tip of my vector, okay?
All right.
So it doesn't matter which one you start with. right? The thing is that if you do one line at the end, the other line has to be drawn at the tip. That's the important part, okay?
Okay.
So I'm going to draw my 30-degree line. Again, as long as possible until they intersect. And I know that this is 30 degrees from the horizontal.
Yep.
But these two lines intersect. And now, what does this give me? If you look at these, you have essentially a triangle, right?
Yep.
And not only that, you have the same triangle that we drew earlier, okay? So now you write down what you know. We know that this is 666 newtons.
Yep.
We know that this angle is 58.9 on the horizontal.
Yeah.
We know that this angle is 20 from the vertical, right?
Yep. And
So
we
do
can
we know?
we can find the angle inside there now.
Okay, yeah.
So in the bottom left of the triangle.
Mm-hmm.
Oh yeah, we can find that angle as well.
Yeah.
We can find most, actually all of them. So 90 minus 58.9 minus 20. 11.1, same angle that we found earlier.
Good. What else can we find?
We can say that the bottom angle down there, 20 degrees. Sorry, it's kind of hard to say where. Let's say little c, we can move that 20 degree over to there, but we have to find the other degrees as well. I'm
gonna try to do an easier one. So we found this 11.1, right? I think it may be a little bit easier we find this one, because we already know that this is a 30-degree line from the horizontal. That means that from the horizontal, this is 30 degrees, right?
Yep.
We also know that this is a 58.9 degree line from the horizontal. That means that from the horizontal, this entire line is 58.9. So can we find this remainder?
Oh, yes. So 58.9 minus 30 is 28.9.
Okay. And what do the angles in a triangle add up to?
180.
Okay, so what is this angle?
Which angle?
This one.
Oh, I see. So if we got 28.9 plus 11.1, that's 40, so it's 140, which is the same as the one up at the top. Huh.
So 180 minus 40, is that what you're saying?
Yep, which is 140, which is the same angle that we got at the top.
Yeah, that's the angle that we got in our first triangle. So we have the same triangle, 140, 11.1, and the remainder. 140, 11.1, and the remainder, right? So it's the same triangle. And now, what I want is your two components. Would you be able to use the sine law or the cosine law for these two components?
So let's see, we have one side and like multiple angles. So I would use the sine.
Okay, sine law. So you use sine law, sine of A over A equals sine of B over B equals sine of C over C. Now you can call them whatever you want, but what you do know is that you have at least one side.
Sine of C and little c.
Okay, there we go.
So, well, I'm just gonna
stay with it
and say that is C.
Okay, that's fine.
So it would be sine of 140 over 666 newtons equals, what are we trying to find? We can find, I forgot which one we called A and B.
I think this was A and this was B.
Yeah, okay. Let's find B. So sine of B is 22.9.
28.9, yeah.
Oh, sorry, 28.9. My handwriting's bad. And that's over B. So now we only have one variable to solve for. So let me turn my page. So we would multiply the, we would first do sine 140 divided by 666. Which is 9.65 times 10 to the negative fourth. But then we would multiply that times B, which would equal B times all of that. Sorry, I'm trying to write this as well as.
Yeah, you want to be careful there. Not sure if this is easier for you, but I would solve for the variable first and then plug my numbers into a calculator to avoid any
Yeah, that would
errors.
probably make more sense. I usually just solve as I go.
Yeah, so I would just multiply both sides by b, so I can have b on this side, and then divide both sides by sine 140 over 666. So what that would give me is sine of 28.9 degrees.
Divided by sine 140,
Mhm.
666. Okay.
Right, so sine by 40 over 666, and I just put the 666 in the numerator.
Sine 28.9. Yeah, that would probably reduce mistakes. So sine 28.9 divided by sine 140 times 666 is 500.7.
Okay, let's round out to 501. So pretty close, right?
Yep.
This is just rounding stuff because our number wasn't really 666, right? It was 665.
Yeah, well, yeah, we rounded a lot of stuff to get here.
But either way, I think we're close enough.
And then we could find, I think, A pretty easily.
The same way, exactly the same way.
Exactly the same way.
Yeah, and then you would get A equal to something very close to 200 newtons, right?
Yep.
Yep. So that's
okay.
That's breaking down a vector into its components. I tried to use the same problem because we already knew what the answer was.
Yeah.
So it was easier, but the procedure is still the same. You start on one side, you draw your direction, you go to the other side, you draw your direction, and where they intersect, you create a triangle. And then from there, it's geometry again.
This way makes less sense, I think, only because I haven't practiced it very much.
Yeah.
But yeah, I kind of prefer the geometrical way.
Okay.
But this was a super easy triangle to figure out the geometry on, so I might not always. Okay. I understand the component method a lot more now, though.
Okay. Yeah, that's good.
Part of it was figuring out when to use law of sines, law of cosines, parallelogram law, triangle law, all that.
Yeah, I would just draw a triangle, right?
Mm-hmm.
Parallelogram law is fine, but I think just
I don't like it very much. I would prefer
is,
to use the triangle law every time if I could.
Yeah, and in terms of sines and cosine laws, it depends on what information you have, right?
Yeah, so for the sine law, we need two angles and one side. And for the cosine law, we need two sides and one angle?
Yep.
Okay.
Yeah.
Cool.
The sine law is the most flexible one. Because you can
rearrange it.
Yeah. But the cosine law, you need two sides. You cannot get away with it, right? You need two sides.
Yeah.
But yeah, that's pretty much it. I think we can call it a day, at least.
Yeah,
for this, and try to do more problems, and then we can get together next week during office hours or something to see your progress.
Are you going to be hosting a review session next week?
On Thursday night, yeah.